So these videos are on quotient groups. We're going to see how we can take the right cosets of a subgroup and turn the right cosets into a group. So we'll start with this example. The group G star will be U32 with operation times sub 32, and H will be the subgroup generated by 9, which I calculated, 1, 9, 17, and 25. And here's a listing of U32. And now I would like to calculate the right cosets of H in U32. Okay, well there's H times 1, which we get by multiplying each element of H by 1. And as always, the right coset determined by the identity is the subgroup. Now we know that since 9 is in the right coset determined by H times 1, the right coset determined by 9 has to be the same as the right coset determined by 1. Similarly, the right coset determined by 17 and the right coset determined by 25 all have to be the same as the right coset determined by 1, and we will call that U sub 1. Okay, H times 3, the right coset determined by 3, we get by multiplying each element of H by 3. So 3 times 1 is 3, 3 times 9 is 27, 3 times 17 is 19 when you're multiplying in U32, and 3 times 25 is 11. And since 27, 19, and 11 are elements of this coset, the right cosets determined by those numbers has to be the same as the right coset determined by 3, and we will call that U sub 2. Okay, the right coset determined by 5, I've calculated here as in the line above. This has to be the same as the right coset determined by 13, 21, and 29, and we will call that right coset U3. And right coset determined by 7, we obtain by multiplying each element of H by 7, which I did, got these 4 elements, and that has to be the same as the right coset determined by 31, 23, and 15, and we're going to call that U4. And we're going to let capital P be the set consisting of the right cosets. So using our shorthand notation, P has elements U1, U2, U3, and U4. Each of these elements is one of the right cosets of H and G. So here is a summary of our calculations. H1 was H9, was H times 17, was H times 25, which we called U1, and so on. So we would now like to define an operation, which I will call star, on the set of right cosets of H. And we would like for P with this operation to be a group. So remember, P is the set consisting of U1, U2, U3, and U4. So we would like to find a way of multiplying 2 cosets. And there's a pretty natural way to do this. Multiplying the coset determined by X by the coset determined by Y, it would be natural to let that be the right coset determined by X times Y. And we're using times sub 32 because we're working in the group U32 here. So this is how we will attempt to multiply cosets. And try a few examples. So for example, U2 star U3. Well, U2 is H, the right coset determined by 3, and U3 is the right coset determined by 5. So using this definition of star, H times 3 star H times 5 would be the right coset determined by 3 times 5. 3 times 5 is 15. There is a slight problem here, though. U2 is also the right coset determined by 27, and U3 is also the right coset determined by 13. So what happens if you multiply U2 and U3 using these representations? Well, H times 27 star H times 13 would be the right coset determined by 27 times 13. Multiplying in U32, that would be the right coset determined by 31. So actually, there are probably 16 possible pairs of representatives for U2 and U3. Right, there's H3 for U2 and H5 for U3, H27 for U2, H13 for U3. I'm not going to try all 16. So which representation of U2 and U3 should we use? Well, you may have noticed that it doesn't matter between these two choices. Right, the answer you get in the first calculation is the right coset determined by 15. In the second calculation, we get the right coset determined by 31. And those two right cosets are equal. They're both U4. So actually, it turns out that it doesn't matter which representation of the right coset you choose, as long as H is a normal subgroup of the group G star. Okay, normality is a concept we haven't talked about yet. So here's what it means for a subgroup of a group to be normal. So we have a group G star. Then H is a normal subgroup of G star if, well, H has to be a subgroup. First, and sort of obvious requirement. Secondly, for every element of G, of the big group G, and every element little h of the subgroup capital H, multiplying A times H times A inverse has to give you an element that's back in capital H. And similarly, for every B in the big group and every little h in the subgroup, multiplying B inverse times H times B has to give you an element that's back in the subgroup H. And actually, item 3 follows from item 2 if we take A equal to B inverse in item 2. Okay, so what happens if G is commutative? Well, if G is commutative and you take an element of the subgroup capital H, and A is an element of G, then A times H times A inverse will be H. Because G is commutative, so the positions of the A inverse and the H can be switched. This is equal to A times A inverse times H, which is the identity times H, which is H. Well, the requirement for being normal is that AH A inverse has to be in capital H. And if G is commutative, AH A inverse is little h. And similarly, for a commutative group, B inverse HB will be an H. every subgroup of a commutative group is normal. And in most of our examples, we will be dealing with commutative groups. Okay, some tools for working with normal subgroups. The first is something that is true for any subgroup. This doesn't depend on H being normal. You have two elements of the group G, and if the first element, little a, is in the right coset determined by the second element, then the two cosets have to be the same. This was really our primary tool in our last module for working with right cosets. Okay, this is true even if H is not normal. And also this, for every element of the subgroup capital H, the right coset of capital H determined by little h will be capital H. This is something that we also knew was true for any subgroup, not just normal subgroups. The last tool is the only one that depends on the group, the subgroup H being normal. Okay, so for every A and G, and for every little h and capital H, there is some element H prime of capital H for which H times A is A times H prime. The second part is similar. Here, instead of having H times A on the left-hand side of the equation, we have A times H. So we think of this as being sort of a commutative law. This says that if you're multiplying little h by A, then you can switch the order of multiplying. You can move the A on the other side of the H. But the element little h may have to change to some other element of the subgroup capital H. So sort of like a commutative law, but not exactly. And this is the only property that requires that H be normal. Okay, so let's look at a proof of part of property 3. So we're proving for every A and G, for every little h in capital H, there is some H prime in capital H for which H times A is A times H prime. And again, we're thinking of this as being sort of a commutative law. The positions of the A and H can be switched, but you may have to change elements of capital H. Okay, so we'll assume that we have an element of G, and we have an element of capital H, where H is a normal subgroup of G. Okay, by the definition of normality, we know that A inverse H times A has to be in capital H. So let's give this a name. A inverse H A. We'll call it H prime, little h prime. It's an element of capital H. And now if we multiply both sides of this equation on the left by A inverse, by A, and the left-hand side will be H times A, and multiplying the right-hand side on the left by A will give us A times H prime. We've shown what we have to show, that H times A is A times H prime. And as I've said a couple of times, we think of this as being sort of like a commutative law for elements of G and H. So it's not true that H times A is A times H, but it is true that H times A is A times H prime for some possibly different element of capital H. Okay, and now here is the theorem that says when you're multiplying right cosets, the choice of the representation of the coset doesn't matter. So we assume G star is a group, and that H is a normal subgroup of G. And now we're taking 4 elements of G, A, B, C, and D, and we're assuming that the right coset determined by A is the same as the right coset determined by B, and that the right coset determined by C is the same as the right coset determined by D. And we're going to multiply HA times HC, and we're going to multiply HB times HD. The result of multiplying HA times HC will be the right coset determined by A times C. The result of multiplying HB times HD will be the right coset determined by B times D. And the theorem says those two things have to be equal. How you represent this right coset and how you represent this right coset doesn't matter if you're multiplying cosets. Okay, the proof is not hard. We'll assume the hypotheses. So H is a normal subgroup of G. A, B, C, and D are in G. And the hypotheses of this if then. So we're also assuming that H times A is H times B and H times C is H times D. Okay, and we're going to show that the right coset determined by A times C is the same as the right coset determined by B times D by showing that A times C is in the right coset determined by B times D. Right, this is our main tool for working with cosets. Okay, we are assuming that the right coset determined by A is the same as the right coset determined by B, and we know that little a is in the right coset determined by little a, so that means little a has to be in the right coset determined by little b, which means that little a is h1 times b for some element h1 of h. Similar thing happens for B, for C. Similar thing happens for C. C will be H2 times D for some D in capital H. Sorry, slight pause here. I noticed a mistake in the slide, which I just repaired. Okay, so similarly, C2 will be H2 times D for some little h2 in the group capital H. So now we multiply A times C using our two representations for A and C. A is H1 times B, C is H2 times D. And now we use tool 3, that sort of commutative law for elements of the group G and elements of H. Right, the order of multiplication here, B times H2, can be switched, but you may have to replace H2 by another element. We're calling it H2 prime of capital H. So A times C is H1 times H2 prime times B times D. We will call H1 times H2 prime H3. And H3 is in capital H because capital H is a subgroup. And this is what we need to assert that A times C is in the right coset determined by B times D. A times C is some element of capital H times B times D. And now, second theorem, which tells us that the set of right cosets of a normal subgroup in G using the operation star that we've defined earlier, is actually a group. And this is not a subgroup of G, because the elements are right cosets. But it is a group. The theorem says it is a group. Okay, the associative law follows fairly easily. We'll look at the first few steps here. So we're looking at multiplying H times A star H times B star H times C with the parentheses around the final two terms of the product. We use the definition of star H times B multiplied by HC is the right coset determined by B times C. And now we use the definition of star once more. The right coset determined by A star the right coset determined by BC is the right coset determined by A times B times C. Since the associative law is true in G, we can rearrange the parentheses. This will be the right coset determined by A times B times C with the parentheses in this orientation. And now we use the definition of star two more times to end up with HA star HB star HC with the parentheses inserted the other way. The identity in the group G over H star is the right coset determined by the identity of G. And the inverse of an element, H times A, is the right coset determined by A inverse. So those are all easy things to show. Okay, the group G over H, consisting of the right cosets of H and G, is called the quotient group of G determined by H. Okay, we're going to try an example here. We will take G equal to U7 times sub 7. H will be the subgroup 1, 2, 4. This is actually the subgroup generated by 2. Okay, we want to know how many elements the quotient group G over H has, and then we want to list the elements without repetition, and then we want to give the table for the operation star on cosets that we've been using. Okay, so U7 has 6 elements, and H3 has 3 elements. So the quotient group G over H has 6 over 3, or 2 elements. Okay, the elements of the quotient group G over H are the cosets of H and G. Here they are. There's H times 1, which is simply H. And that's the same as the right coset determined by 2 and the right coset determined by 4. And the other right coset is the right coset determined by 3, which I calculated to be 3, 6, 5. So this will also be the right coset determined by H, determined by 5, and determined by 6. So G over H consists of the 2 right cosets, H1, H3. I mean, we could use any other representation here for the right coset determined by 1, and similarly for the right coset determined by 3. I've just picked these. Okay, so here's what G over H is, the quotient group G over H. These two right cosets, H times 1 and H times 3. And now we're going to calculate possible products, all possible products of these two things. So for example, H times 1 star H times 1 is the right coset determined by 1 times 1. We're working in U7, so this is multiplication in U sub 7. And 1 times 1 in U sub 7 is 1. H sub 1 times H sub 1 is H sub 1. Well, as we knew, the right coset determined by the identity is the identity in the quotient group. Okay, H3 star H3. By definition, that's the right coset determined by 3 times 3. 3 times 3 in U7 is 2. And so we get the right coset determined by 2, which is the same as the right coset determined by 1. I want to write it this way because I'm using that representation in my description of the group. Okay, and H1 star H3 is the same as H3 star H1 is the right coset determined by 3. And now we're in a position to write down the table for the operation star on the quotient group G over H. The operation star, the row headings are the two elements of the quotient group. The column headings are the two elements of the quotient group. And here, for example, is the result of multiplying H3 times H3. We got H1.